So, welcome to week 6 live session of molecular spectroscopy of physical chemist perspective. Thank you for joining on this postponed session. Actually, the session today is Saturday, right? So, thank you again for joining in such a odd time. Uh, Today, our session, I will try to keep it short. So, mainly today, we are going to discuss something about the Raman spectroscopy that has been discussed in the week 6 lecture series. And I will just touch upon the prospect of symmetry and group theory that has been started on this week. But I will try to cover the main thing, the main symmetry part, maybe on the next discussion session, so that we will discuss symmetry for only, I guess, only 1 week, maybe the next one. We'll try to cover as many as questions that can the theory part on the next day. So mainly today we are going to discuss the Raman spectroscopy part and the week 5 assignment. We'll start with week 5 assignment. It's long due. I think we have already submitted it. And it was quite easy, right? It was based on those transition moment integral, Eyring equation and all, and the laser, right? Two-level system or some three-level system, something like that. So let us start. So the first question, in order to get a good spectrum, this is just about we have touched upon this many times. So speed of acquisition should be fast. Not really, right? What should be the answer if to get a good spectrum? Averaging time should be long. Yes. So if we
Yes.
can take this acquisition time for long, or we can average at one point for long, then our spectra will be less noisy. One thing is that, and then slit width should be small. Um,
It is correct, sir.
yes.
Sleeping.
So slit will actually leads to your correct resolution. So suppose you have a very high slit, then you lose the information, resolution information, right? You are not, so suppose your maxima can be shifted like that. So that won't be a good spectrum, right? Means how can we get a good spectrum? So for that, the second part would be good, right? The Where is my cursor? Oh, I have not connected. Okay, connect. Sorry. So obviously, the first part would be the averaging time should be long.
Two
Uh,
and
sli-
three is the correct answer, sir.
2 and 3 are the correct answer. Why not
Yes.
fourth one is the correct answer? Concentration. If the concentration is long, then you should get greater
Yes.
intensity, right?
Yes, yes.
But
Concentration means you want to say the concentration of the this analyte or
analyte
something
or
like that.
yes, suppose the fluorophore. Suppose we want to measure a should the
Yes.
concentration should be high?
Then maybe the absorption will be higher. That is unwanted.
Yes, if the concentration is high, then what can happen that you can again face the inner filter effect, something like your so your excitation light cannot pass through the media. The If it is highly opaque, I mean, suppose you have a 1 molar concentration or some molar concentration, millimolar, even sometimes millimolar concentration. So what can happen that your excitation light is not able to pass the so from where your signal actually get extracted. If you think of the cuvette and suppose you are I'm mostly in fluorescence spectra. Suppose this is your excitation light, this is your sample holder, and at 90-degree right angle, your this is your monochromator, emission monochromator, right? And then your detector. Obviously, I am not discussing about the excitation monochromator and source, right? So if you see, if your concentration is very high, but you see your emission is being collected from the middle of your sample. So if your excitation light, if your concentration is too high, then what will happen? First thing that your excitation light, whatever is intensity at this length, and at this point the intensities are different, right? So at this point your intensity would be very very minute. So because your all of the intensity has been uh, taken away by the molecules here. So this is one kind of inner filter effect. This is known as the primary inner filter effect. What could be the other thing? So if your absorption spectra and emission spectra both are very close, or they have a considerable overlap. So this is your absorption spectra and this is your emission spectra. Then if they have a considerable overlap, it could be there, right? So if that is the case, then suppose you have a very high concentration here, then what will happen? That whatever minute excitation is there, it is there. Suppose now your this molecule is trying to emit, so this is emitting something, huh? But when your concentration is too high, then the nearest molecule, what they will do, they will try to reabsorb this part, because this is actually in the range of their absorption, right? Absorption spectra. So they will try to reabsorb that part. So this is reabsorption of emission. So what will actually happen, that instead of your proper or whatever your ideal spectra would have been, you are going to get some rate shifted spectra. So this part you can't. So this is your actual spectra, and this is your rate shifted spectra. Okay. So this is coming due to your secondary inner filter effect, and most of the
That's why,
time, yes.
sir, that's why Stokes shift is preferred for this kind of emission.
Nee, depending on your application.
Yes,
Suppose
yes,
you
yes.
want to see you want to use your probe in biological application or something like that. Depending on your application, uh, your stroke shift should be high. See, the fluorescence molecule like rhodamine 6G or coumarin. Coumarin still have a moderately high stroke shift, but fluorescein, if you see, let me go to in Google and let us Google the. I hope you can see my screen. So let us
Yes.
Google the spectrum, absorption emission spectrum of rhodamine. Rhodamine 6G is a dye which has a quantum yield of 94% almost. So that is a very high quantum yield. See, in the case of rhodamine 6G, I hope you are able to see this. Let us only see here. See, the Stokes shift is very, very less. And that is the reason the quantum yield is also high, I would say.
Okay.
Why? Because the gap between the S1 and S2, or from where the emission is taking place, there is very less non-radiative processes are there. So that's why the Stokes shift is very less. You will see higher Stokes shift when there is some excited state processes going on. So I can draw a schematic for you. Suppose this is your ground state, huh? And this is S0. So from here, your locally excited state or S1, suppose S1, locally excited state, huh? This is S1 locally S1 for locally excited state. So this is where you have excited your molecule. This is assume like this, huh? Now there is some excited state processes. What is the excited state processes? There can be excited state intramolecular proton transfer. There can be excited state cis trans isomerism. There could be a charge transfer process in excited state. Huh? Due to that, a different excited state can be. generated from your locally excited state. So it can be generated, and it obviously as some thing is happening, so obviously energetically that state will be energetically relaxed. Whatever the new state has been formed, it will also be S1. S1 of your relaxed state. Even it could be a triplet state. Depends on your excited state process. Right? It could go to a ISC process, go to a triplet state, something like that. Right now, I am still in the approximation that it's S1 state, but some other excited state process has taken place. Now, your emission will take place from here, fluorescence, from this S1 state. Now you see the energy gap between your, this is suppose delta E1 and this is delta E2. Okay. Now your delta E1 is obviously greater than delta E2. Now your lambda 1 of emission, what could have processed from here, your lambda 1, and this is lambda 2 suppose. Huh. So your lambda 1 will be very very small than lambda 2, right? So you see your stroke shift, possible stroke shift is very very high when there is a excited state process. But for, and these excited state processes are often going through some non-radiative pathway, right? So and another thing, whenever your some excited state process is happening and your relaxed excited state is formed, then the energy gap between these two, obviously what I told, delta E2 is less than delta E1. So there is a energy band gap law. Whenever this energy band gap is less, then there is exponentially there is a chance of non-radiative process grows exponentially. So your non-radiative pathway enhances. So that's what I'm trying to say, that when there is a stroke shifted emission is taking place, more often than not, the your emission quantum will be quenched. So this is just a outside discussion what we just did. This is not really point of the today's discussion, but I hope you got the idea that what is when the stroke shift is very less. Your like for fluorescein or rhodamine, why the quantum yield is very very high. Um, and other thing. And obviously that takes place because that excited state is very stable. Your sometimes these molecules doesn't go any excited state process. Those are very rigid molecules, something like that. So there are multiple reasons can be associated with it. But whenever there is a very long excited state, sorry, very long stroke shift, it is assumed that there are some excited state processes that is happening. Okay, so that is one part. Now, let us come back to our question number one. So, so we understood, right, that when
Yes.
the concentration is very high, we are not going to get the actual spectra. So that is actually not a good idea to get a very high, extremely high. So if it is written moderately high, then we could have maybe click it a correct option. But it is always uh, it is better to keep your concentration very very less. Not for not only for fluorescence spectra, even for absorption spectroscopy also. So your absorption spectroscopy is nothing but your something 10 to the, so what is that? Your A is epsilon CL, but what is this? This is your logarithmic of
I zero
I
by IT.
I0 by IT.
Yes.
So you're actually I0 by IT, if I write it in terms of 10 to the power epsilon CL. So you will see that if if you increase your concentration, then your I transmitted is going to be very less in order of something like 10 to, so it will decrease in order of it will decrease in order of 10 to the power something. So your OP, so whenever you if you see your absorbance 0.1, it is enough. So when you see your absorbance is 1.0 or 2.0, those are actually not good, right? So so that means your I0 by IT, so this is 10 to the power some 10,000 or 20,000 epsilon value would be there. Your AL is something like that. So what does that mean? That your if your concentration is that much, then that is not a happy situation. You should always work with very less concentrated sample. Okay. So now let us come back to the question number two. And why the speed of the acquisition should be fast, should not be fast, then obviously you will get a noisy spectra. Okay. Now the second, time to break a bond typically is 100 to 200 femtoseconds, right? So this is coming
Yes.
from the Eyring equation. Uh, Let me write down the name once. So Eyring equation, and with the assumption that the partition coefficient for the product and the reactants are almost equal and one, close to one, and your energy, it is non-activated process, means the activation energy is also zero. So by that way, it will come. You will get something like the rate constant, and your lifetime would be one by that rate constant, and it will come something like 170 femtosecond or something like that. That's where the femtochemistry actually began, due to the by actually the invention of laser, and then ultrafast laser, and then applicability of application by Professor Ahmed Joel and all. Well, okay. Now, question number three, two-level systems cannot be used to make a laser. Why?
Population inversion cannot be achieved.
Yes. How does that graph actually looks like? If I plot it, maybe in N1 by N0 or N1 N NM by NL, right?
Yes.
Sorry, NM by N, NM by N with time. So how does it look like? It will look like something like this, and
It will
it will
never achieve
be,
point 0.5. Point
yes,
0.5.
it will be less than half. So
Yes.
it is the limiting value. So population inversion cannot be achieved is the right answer here. And with the same graph, we can answer the second part. For a two-level system, the ratio of population of the higher and lower energy state must be
Less than
it must be less than one,
1.
right?
I choose that option, this one, but in the answer sheet they provided it is point 0.5.
I think they have taken this NM by
Yes, yes,
total. I think
yes,
this
yes.
is
But
the total.
yes, yes.
Okay. I'll let them change the answer. So what should so if NM by NL
And then
should be
less
greater
than
than one for a population inversion system, but it is not the case for when I should write. This is for population
yes.
inversion case. And for a two-level system, your NM by NL is less than 1, right?
Yes.
Okay. So, okay. Then question number 5. A and B are Einstein coefficient and for spontaneous and stimulated emission. Okay. Right. Now KNR is a non-radiative decay constant. So lifetime of an excited state after light is switched off
Yes.
is
A
the
plus K in
inverse.
inverse. Fourth one. A plus K in
Yes. Why B would not be there?
because stimulated part is not there. No? That's why.
Light is switched off. If the
Yes.
light is on, then it would have been A plus B
Plus
plus
plus.
KNR.
Yes. Yes. Yes.
Yes. So this is the right option here. So I should write it once here also there. tau f, or maybe only tau lifetime, fluorescence lifetime, it's fine, is 1 over a plus a n. Now 6. A laser spectrophotometer has a superior resolution than ordinary spectrometer because the laser light is
Monochromatic, highly monochromatic.
highly monochromatic. When it is not a highly monochromatic, if I would say the laser is ultra fast, means it's
Ultra fast spectroscopy.
yes. Then it's not really a monochromatic. It's become a polychromatic laser, right? The fundamental emission is very high, intensity would be high, but it's not really a monochromatic. And one thing is that in our mind it is something like we always use something like we always think of a laser excitation as a delta excitation. So I drawn a wrong thing. Suppose delta excitation means the width is very small, but it is never like that. In this is in time domain, obviously this is in time domain, what I'm trying to say. uh, so delta pulse is something like at time zero, the excitation is high, then it falls off at both end of the zero. But, but it is not never a delta pulse uh, because it's not possible. Theoretically, it is possible.
Yes.
Experimentally, it is not. So anyway, now question number
No,
seven.
sir, theoretically it is also not possible because there is some kind of uncertainty. Uncertainty still exists in the
Right,
excited state.
right. That is due to the natural width of
Yes,
the
yes,
natural
yes.
width, right? Yes, natural line. Right. So question number seven. In order to get femtosecond resolution in a pump probe experiment, the pitch of the screw on which the translational stage is mount has to move with a resolution of, do you know how
Nano,
much?
nanometer. I choose nanometer, but they provided micrometer. Sir,
Yes,
if you solve the problem,
yes, I will
if you
solve. I will solve you the problem, but let me first show you how this. Uh, Maybe I will first show you how this. Let me join with my mobile, and I will show you how this. um uh, Actually, this delay stage actually looks like. Do you want to see it? Then I can
yes,
join.
yes.
Then I will join it from my phone. Wait. Let, so you are seeing it for the first time. And actually, I don't have a camera with my laptop. Go inside the pump probe spectroscopy room. So how can I? So this is what a pump probe setup looks like. Can you see it, Sumitro?
Yes, sir. Yes, sir. I can see.
So this is the spectrometer part.
Yes.
I will discuss it maybe on a later day. So this is where the pump and the probe actually collide. This is your sample holder. So maybe on a later day, I will show you how it works. But this is what a delay stage looks like. This is what. This is something a 1 feet long delay stage, huh? And
Yes.
based on a pitch and a screw of that,
Yes.
you can see this metallic thing there. It
Yes. Yes.
rotates. When it rotates, this is the retroreflector.
Yes.
Uh, I hope you can see the retroreflector from here. So actually, what happens? The light actually falls on one side of it and then
Okay.
comes there. So this is a V kind of a mirror. So
Okay.
light falls off one stage, then comes here, and then it comes here. So and what happens that when this pitch actually the screw actually moves, so
Yes.
then this can go from here to there on a very fine steps, and those steps are actually microns. I will show you why that is microns. I will
Okay.
solve the numerical part, but I
Yes.
hope this is what it looks like. So
Yes.
for that, what I'm going to use the mathematics is that if I move the mirror by s distance,
Yes.
then the light has to move
By
2s,
twice. Twice. Yes.
because it is something like a V kind of a mirror
Yes.
kind of thing is there. So let me go back to the laptop and then I will solve the numerical. I hope
Yes. Yes. Yes.
that
Thank you,
will.
sir.
I hope you have. So this is so the actually it was a very big setup. I was not explaining all the things. I just wanted to show you. Just wanted to give you a feel of that, maybe. Huh? So can you hear me now?
Yes. Yes, sir.
Yes.
Yeah.
So actually, the retroreflector, it is something like this kind of a mirror is there, V kind of. What happens is that the probe light falls here. This distance is very less, negligible, and then actually it comes out. Huh. So what actually happens is that this retroreflector is placed on the delay stage, and the delay stage can now move depending on the pitch of the screw. Huh. So
Yes.
suppose the delay stage is moving s distance.
Yes.
So if it moves to this distance, so this is actually s. So actually what happens, your light has to path extra 2s distance. If delay stage moves s distance, then light has to. So this is something like your the part what we actually Michelson interferometer. Similar to
Interferometer.
that,
Yes.
light has to travel 2s distance. So what actually happens that now you need to get a femtosecond resolution. So between 2 points, two time points, it should be femtosecond, 1 femtosecond. So 1 femtosecond is 10 to the power minus 15 seconds. So your light should, so your 2s distance divided by your speed of light
Yes.
equals to your, so the distance should be such, it should be traveled by the light in 10 to the power minus 15 seconds. So this is c is something like 3 into 10 to the power 8 meter per second. So you this that con. something like 3 into 10 to the power minus 7 meter, and actually 3 by 2 we can think of it as 1.5, right? 1.5, which is something like 15 micron, right? 10 to the power minus 6, no,
No, point one five micron.
point 0.15
Point,
micron, 0.15 micron, right? So this is a micrometer.
no, sir. The thing is that you are asking about pitch of the screw. Pitch is the smallest part of the screw, means your total distance will be 0.15 micron, but you
Hmm.
have to revolve the pitch, sir. Pitch is the
Hmm.
smallest unit. Let's say what I'm talking about. Let's say I have a scale, okay, in
Hmm.
1 centimeter. It
Hmm.
has means it is 1 centimeter is divided into 10 parts. Is there?
Right, millimeters.
Yes, yes, mm. So
Hmm.
pitch will be lesser than your micrometer. Otherwise, how can you, if your pitch is like say in micrometer, then you cannot shift 0.15 micrometer. Means your
Hmm.
smallest unit is 1 micrometer. What I am saying, is it clear to you, sir? I am saying that let's say you want to change 0.15 micrometer,
Hmm.
but your
Hmm. Hmm.
smallest
Unit should be
pitch of the
lesser than
screw.
micrometer. You are saying
Yes,
it
yes,
should be
yes, yes,
lesser than
yes.
micrometer.
Yes, sir, that's why I choose a nanometer. That is the closest one to this thing.
Okay.
Angstrom, it maybe angstrom maybe angstrom, but that's why I choose nanometer is the option.
Okay. Then I have to discuss once with Professor Datta because I don't think the pitch will move nanometer. So it is if it has to move a nanometer, then it would we are asking too much from a mechanical rotor. Actually, what happens that the instrument we have, the resolution is not really 1 femtosecond. It's something like the minimum the instrument you just saw. Something like for each step you can go to uh, something like three femtosecond, 3.3 femtosecond, something like that, the minimum. So actually it is something like zero point 0.5 micron per move. So, so it can move zero
But
point
sir,
0.5 micron, but it cannot move nanometer. So the
no, sir, I am not claiming that it should be it must be lesser than your micrometer. Means your total distance means once you revolve the full turn, then it will move.
Mhm.
It must move 0.15 micrometers. So the pitch will be lesser than that.
Right. So I think the
That's
unit should be lesser than micrometer.
lesser than
So and
micrometer.
for here it is only option is nanometer. One option is angstrom. That is
Nanometer or
too much we
angstrom,
are asking.
maybe.
Okay,
But that's why
okay,
I choose nanometer. It is the closest answer. That's why I choose nanometer.
okay. So just let me mark it here. I will ask Professor Datta once about it, and then I will confirm it maybe on the next day. And not on the next day, next day, because I think Datta sir is not here for the next week, for this week. So Monday, I don't think I will meet him. The next class is on Monday. So maybe on the next Monday, I'll discuss this once. Remind me once, huh? And if I forget. So I'll
Sure.
try to ask him this. Good observation. Yeah. Thank you. So it should be lesser than micron. So lesser than micron is what? So I'm not asking in the terms of here. Like here it is nanometer. So it is something like 10 to the power minus 7, 10, zero point 0.1 micron. What do we say that? Do we say something like that? I don't think so. So I'll ask Datta sir that what would be the proper answer. Okay. Okay.
Okay, sir.
Okay. Now let us actually solve this question once and for all. I have asked this question for a long time, but could not solve it properly. I just gave you the hint, but I wanted to solve it once. So let us solve it. So this is based on the question is determine your uh, wave number at equilibrium wave number and the force constant, the anormality, the 0 point energy, the bond dissociation energies, two dissociation energies dE and DO or D naught for hydrogen, molecular hydrogen. The fundamentals and the overtones are listed. So first of all, let us remind. So if we go with a simple harmonic oscillator model, then our potential energy follows this parabola, right? And the energies looks like something like this, and energy gaps are equal, right? And
Yes, sir.
this is our equilibrium. So this is y-axis is energy. Let us write potential energy, and this is our x. You can say x. That is the deviation from the equilibrium bond length, and this is here something like I should write R0 or R equilibrium, something like that. So in this case, what is the energy? So this is E0, so this is state 1, state 2, state 3, sorry, state 0, state 1. So V equals to 0, V equals to 1, V equals to 2, V equals to 3. The energy is like E1, E2, something like that. What is the energy of here? This is E. So if I write in terms of E new, E0, in terms of centimeter inverse, then it would have been half
Omega
nu.
new one.
Yes. Then if it is E1, then it is 3 by 2 nu, because it is actually V equals to V plus half nu bar centimeter inverse, right? Let me write centimeter. So this is the, and what is the gap here? So let me write actually nu 0. Let me write because the new oscillation, not nu 0, new oscillation. So the gap is the gap between or the transition between this was 0 to 1 is near 0 oscillation. This centimeter inverse, whatever unit it will come. Now, when we introduce the enharmonicity into this, so what will happen? Your potential energy now follow the Morse potential. What it looks like? It looks like something like up to certain part. It looks like the parabola, not exactly, but then at certain energy or certain quantum certain vibrational level, the energies become very very close. First of all, the when we bring enharmonicity into the factor, suppose this is the distance, this is the equilibrium thing, and this is your potential energy, the energy gap starts to decrease at very high value of v equals to 0, and it actually becomes very very close. And after this dissociates. If we give this much energy, then the bond will dissociate. So that is DE. What is D0? D0 is the energy gap here. Energy gap between your 0 point energy and the dissociation total.
And this
Uh, yes. So what are the things we need to get? We want to determine DE, we want to determine D0, we want to determine force constant. Force constant is related to by 1 by 2 pi. Sorry, I am writing a wrong thing. Your wave number is like k by m, right? Or mu,
yes,
the reduced
mu.
mass.
Yes.
So if we, and this is something like nu e most of the time, because we have already introduced the enharmonicity into the equation. So one more thing here, your energy, how does it looks like now? Your change EV when the anharmonicity is introduced, then your uh, first of all, when there is no anharmonicity, there is the concept of dissociation energy is not there. The dissociation energy concept comes when the anharmonicity is there. Okay.
Right. Yes.
Then your energy is something like V plus half. Now it is not new oscillation. We term it as the wave number at equilibrium. Then minus V plus half square of it nu E. And this is your anharmonicity. So your actually anharmonicity is the product of nu E and Xc, and this is Xc is your anharmonicity constant, and this doesn't have any unit, and it is a very small quantity. Okay. Now what is next? Then let us get the energy of zeroth energy, that would be similar to half uh, nu E minus one
1/4
fourth of
nu
X.
V X.
Right? And E1 is
This
3
3 by
by 2 nu E
minus
minus
9 by
1
9 by
9
4.
by 4
Yes.
nu E Xe. Now the point I have earlier touched is that Xe is very small.
Yes.
So the energy gap, let me also once for this when the anharmonicity is there, it is like nu E minus 2
2 nu E X.
2 nu E Xe. Now
Yes.
as Xe is very small, we can assume that these two are actually equal. That this thing is equals to your nu E minus 2 nu E Xe, because your Xe is very small. At this level, the energy gaps are almost similar. But when your V get very high value, then only your then only you can see the changes. You can't see the changes for 0, 1, 2, 3, something like that. Very high level of V, you are going to see the change, because then the square, as the square, it is changed by the square terms. That's why it will be very high. Actually, your X is very small here. So because of that, we can say that the energy gap, the first energy gap, we can take it, we can assume that they are equal. From there, what we can see is that the first energy, that is fundamental, is given. So as fundamental is given, then we know this is given 4161.14 centimeter inverse. So your new E is given.
Sir, we have to take the whole formula, otherwise we cannot find out the enharmonicity constant.
Mm, yes. So acha, I got your point. So what I'm trying to say, we have
Yes,
this
yes,
value.
yes,
uh, we actually don't. One second. Yes, we have the. So this is your fundamental, right?
yes,
So this is what is given. Then
yes,
what is your 220? 220 would be, let
yes.
us E2. Let us write E2 here. E2 is 5 by 2
5 by 2 nu E
nu E minus
minus
25 by 4
nu
X
E X.
nu E. So your delta E 2 0 to 2, that is
Yes,
your first overtone, that is
yes. 2 nu
2
E
2 nu E minus 12, not 12,
6
6 nu E
6
X
X.
E, which is something like 2 into nu E. If we common take a common, let us not take common, or maybe we can, let us keep it like this for now. So these values are given. So we want to know nu E and Xe, so we need two equation for two unknowns, right? So nu e minus 2 nu e xc is given, which is 4161.14 centimeter inverse. And what else is given? It is 2 nu e 1 minus 3 nu e, sorry, not nu e, 3 xc is given, right? I will prefer to write it in the form we got. 2 nu e minus 6 nu e xc, that is 8087.11 centimeter inverse. Actually, there is something called Barge-Sponner plot.
Okay.
You can find it in the Atkins book, but I don't think we don't have to. We have to go to that for solving this problem. And that
No,
is
sir,
some.
just simply, sir, divide equation 1 by equation 2, you will
Yes,
get rid of this new e. And from that, you can find out the xc. If you find,
yeah,
just simply divide equation
yes.
1 by
So this
equation
is
2.
your equation one. No, what I'm trying to say is there is a concept of Barge-Sponner plot where you
Okay.
plot your energies with your V or V plus half, something like that. You can check as in the Atkins. I'll write what I'm trying to say. Budge Spooner plot. So, but I'm not going into that. That is not required. But something like this is also there. Budge Spooner. But we don't have to go there, as you say. That we can take 2 by 1, and what we will get is we'll
We'll get rid
get,
of new e.
yes. So we will get 2 minus 3 xc divided by
2
1
minus
minus 1 minus 2 minus 6, right?
6.
Yes.
Yes, yes.
2 xc is equal to, so I will require maybe a code.
1.94.
1.94. Thank you. So 1.94. So we can take uh,
This leads this
hmm,
leads to xc equal to 0.028.
point
028.
028, and it is a unitless quantity, right? So,
Yes.
so your xc or this is something like that, and you put the value in any of the one equation, and you are going to get nu e. Let me write the equation once, and then I will take the value from you. Nu e into 0.028 4161.41, right? Sorry, 14 centimeter inverse. So
Yes.
what the new E is?
It's 4407.9 centimeter inverse.
4407.9
9.
centimeter inverse. So you got new E and XE. So first of all, we have got new E. Huh? Now we got new E and we can put it to this equation, right? Then we can get the force constant. So let us do that. Wait, I need to pick one call. Sorry. Ankit. Ankit, I am in the middle of the class. I'll talk to you later. Yeah. So nu is already given. So your force constant is K, is actually 4 pi square nu E square. Then actually your mu. Obviously mu for your
C
uh,
square also, C square also be there.
yes, because this is new bar, right? So you need C. If it was only frequency, then 1 by 2 pi was good. But as it is wave number, you need 1 by 2 pi C. So you also need C square. So your mu for hydrogen, how much? 1 into 1 by 2,
Half,
0.
half, half. half
zero
AMU.
point 0.5 AMU, right? And that
Yes,
is
yes.
1.66 into 10 to the power minus 27, sorry, 31 kilogram, right? Am I, no, minus 27, right? I am going a little wrong here. Minus 27. So this is in kilograms. So let us write the value once, 3.14 square of that. New E we got 4407.9 centimeter inverse. So I will write centimeter to the power minus 2. Then also new on, let us write c square first. C square is 9 into 10 to the power minus 20 centimeter
Centimeter.
square second minus 2, right? And then comes your this new the reduced mass. Let us write in this fashion, and I will directly write the value. First of all, your centimeter to the power minus 2 and centimeter square gone. It is kg second to the power minus 2, which is the unit of your force constant. You can even write it in terms of Newton meter inverse also, but doesn't matter in this case. Let us get the value from, let us
Outcome
calculate
is the outcome is, sir, 573 Newton per meter.
Okay, so
Seven,
573
yes, Newton per meter.
Newton per meter. So obviously kg second to the power minus 2 is itself Newton meter inverse, because if you know that Newton is what? Force. Force is mass into acceleration, meter second minus 2 into meter, right? Uh,
Yes, yes, yes.
so your Newton, and so this is your Newton, and then if you multiply with it by meter inverse, then you get kg second to the power minus 2. So that's you don't need to change the unit. So this is what 572 is coming as your force constant. So let me highlight the values what we are getting. First of all, we got the value for the equilibrium frequency, right? Then we got the value for the force constant. For that, obviously, in between we need to get the reduced mass. And now for anharmonicity, what would be the value? Anharmonicity would be multiplied by your new E you know. So anharmonicity is what? Xc into nu. That is your 4161.1 sorry 4407.9 of us 0.028 4407.9 centimeter inverse. So I am not writing the value, but this is what come as a anharmonicity. Now 0 point energy. 0 point energy is this E0.
Yes,
So
yes.
half of this, even not half of this, I think it would be better. Uh, so what do you think? Your 0 point energy, should you write it in terms? I think it is better to write in terms of uh, when the your actually, oh, actually, in this case, you don't have to think of the first part, what I actually was discussing. And so this was for the previous question that, so you actually did not require this equation. Let me highlight it in other color. So this equation was not at all required. for this part, right? So this equation is not required for this. So you can only get it from only from the anharmonicity thing. Anyway, so now you want to 0 point energy. 0 point energy would be your E0, that is your half of 4407.9 centimeter inverse minus 1 by 4 into this 0.028 into 4407.9 centimeter inverse and check how much you are going to get. Okay,
2173 centimeter inverse.
2173.1
7.1. Yes.
centimeter. Using this whole thing, right? Half into 4407.9 minus 1 by 4. Or let me once actually check it. I will start with the anharmonicity value, that is 0.028 into 4407.9. It is something like 123.4 centimeter inverse. And then um, 4407. Yeah, 2173.1 centimeter inverse. You're correct. So this is your 0 point energy, right? And we need to remember another equation. So that is the relationship between your anharmonicity constant and your dissociation energy, that is given by mu E divided by 4 dE. So from here one can calculate the dE. The dE would be 4407.9 centimeter inverse divided by 4 into 0.028 centimeter. How much will be the answer?
39357 centimeter inverse.
393.957.
39357 centimeter inverse.
It is a large value, right?
39357, not 9, not with you. 39357 only.
357. So this is not bad, right?
Yes.
It is correct right now, I hope. Yes. So this is going to be your DE. Now D0 would be DE
Minus E0.
minus the PE, 0 point energy.
Yes.
So that would be 393. Let us calculate. 393.57 minus 2173.1. So maybe it is something like 3700,
84.
7,184.
Centimeter.
Yes. So with this one question, one can get all the concept or all the formula they can remember from this question. So I thought that at least for once we should solve it. Okay. With that, let us come to actually today's main discussion, that is your Raman spectroscopy or Raman scattering. So first of all, the main question we asked was huh? Um, one second. So the main question we asked during the um, mm, uh, initial days of microscopic when we are studying microwave spectroscopy and infrared spectroscopy, that first of all microspectroscopy is when we can see a microwave activity when there is a permanent dipole moment, and now when there is a change in the dipole moment during the oscillation, then
Then
it will be
I
infrared active.
yes, I
But
electric.
yes, now if our molecule doesn't have a permanent dipole like nitrogen, oxygen, most of the diatomic, homonuclear diatomic molecule, not most, all of the homonuclear diatomic molecule, how can we know the bond distance? Or how can we calculate the bond strength, something like that? The bond strength will come later, but how can we calculate the bond length? Because we know that bond length will come from the equation of rotational constant B, right? B is so that rotational constant B, if we remember, rotational constant B was H by 8 pi square I. I was moment of inertia into C, right? In centimeter inverse unit.
Yes.
So from here, I is your mu r square reduced mass into the bond length square. So from microwave spectroscopy, if we know we can get the transitions are correct, then we can get the idea of the bond length. But for homonuclear diatomic molecule, it was not possible because the permanent dipole moment was zero. Now that problem is actually solved by Raman spectroscopy. We'll not obviously not go into the deep of the selection rule and all, but this Raman spectroscopy is applicable in the rotational spectroscopy as well as vibrational spectroscopy. First of all, the how does the Raman so in case of Raman spectroscopy, we are not dealing with, so in case of spectroscopy so far, what we are doing is that we are dealing with the radiation, means the electric field of the radiation with your uh, your dipole
Dipole.
moment of the matter, right? Or the molecule what we are dealing with. Now we are not exactly dealing with the dipole moment, we are dealing with the induced dipole moment. As we discussed that time also, there could be many interaction possible, right? The maximum was dipole, the interaction between dipole moment and your dipole moment and your electric field. Another interaction possible is induced dipole with your electric field of the radiation. Now that induced dipole moment mu I is can be written as alpha E. Alpha is what? E is what?
Electric field.
Electric field,
External electric field.
external electric field. What is alpha?
There is the atomic polarizability.
Polarizability. Now it could be associated with other terms as well, right? Beta E square, gamma E cube, and so on. What are these? Beta and gamma. These are higher
Higher
order
order polarizability.
polarizability,
Yes.
hyperpolarizability of first order, second order, is like so on. And the values of gamma is very less than beta, very less than alpha. So the order is such. So to get this kind of hyperpolarizability, your electric field should be very high, and that is possible when only you can use a very high intense laser light. So with a normal light source, so even alpha is very weak, right? So with a normal light source, this induced dipole moment is very, very less. So that's why for a Raman spectroscopy, you need a very highly intense monochromatic laser source. The monochromaticity is not related to the electric field right now, but to the intense part is very important here. So the more intense laser light you use, more effect of the beta and gamma will come into the place. But for the discussion for now, let us only deal with the alpha E. So with a moderate light also you can get some induced dipole moment. Okay. And that dipole moment is what now your alpha can be written in terms of alpha 0 plus some constant into your sine function of a uh, some molecular motion, which could be your rotational motion or could be vibrational motion, periodic motion, as Sir also discussed, right? And obviously E is in terms of 2E0 sine 2 pi nu t. Okay, and this nu is nu L, frequency of the light. Actually, from here, what you can see is that you are going to get two kind of term. One will consist of, so maybe I will write it here once. So that would be your 2 alpha 0 E 0 sine 2 pi nu L t, right? One term would be like this. Another term would be what? Another term would be your 2, actually your 2 would not be here. A E0 cos 2 pi nu L minus nu M t. Another would be minus A E0 cos 2 pi nu L plus nu M t. Okay. So this is what the classical picture actually looks like. So if you see what is happening here, when you consider this, your frequency of the light is not changing, right?
Yes, yes.
Here what is happening? Here frequency of the scattering light. So here what is happening, that the scattering light have same frequency. Here what is happening, scattering light has less frequency. Less frequency than what was incident. Then here you're scattering. I'm not talking about the intensity. I'm talking about scattering light frequency has more frequency. Means it. So you can see, this is known as Rayleigh scattering, right? And it depends something like lambda to the power -4, something like that. That right? Why the sky looks blue. One of the reason is the main reason is Rayleigh scattering, right? Anyway, uh, then this is your part coming from the Raman scattering. So you will see your scattering frequency is changing. That means whatever interaction is happening, that interaction is inelastic scattering. So for your Rayleigh scattering, it was a elastic scattering, so there was no change in the frequency, and here the frequency is changing. In one case, it is decreasing, and in another case, it is increasing. So where the frequency is decreasing, that is known as, so frequency is
Stokes,
decreasing.
Stokes, Stokes
Yes.
theory.
How can you remember for a longer term? You remember this frequency is decreasing, your wavelength is increasing,
Yes.
right? So when so you what we say about the fluorescence, it is Stokes shifted. So your fluorescence come at a higher wavelength than the absorption. So by that way, you can always remember that when the frequency is less, lambda is more. So this is Stokes shifted Raman scattering, and this is anti-Stokes. S should be always capital. Stoke is a scientist name. Stoke. Raman scattering. Okay. Now, so this is the basic thing. This is coming from the classical part. Uh, Obviously, there is a quantum mechanical treatment is also there, but that is easier than this in terms of the photons. So that I'm not discussing that. You can find it from the Banwell's book. That is even easier from this. The it is already easier. That treatment is even easier from this. Anyway, so there are two kind of Raman spectroscopy we are going to deal with. One is rotational Raman, and another is going to be vibrational Raman, because these are the two molecular motions we have dealt with. And you have seen that in this equation, this new m could be either vibrational or rotational, but it should be periodic. Anyway, but here for the rotational Raman, what is the uh, selection rule? You
Plus
remember?
minus one, plus minus. It can take any values.
No, for rotational Raman, it is plus minus 2. The rotational Raman was plus minus 2, wasn't it?
Okay.
So in that case, and I did not discuss it yet. So this is your rotational. Suppose this is your rotational levels, and this is your virtual state. What is the lifetime of a virtual state?
Very less.
Very less. It is zero. Actually, theoretically, it is zero. And what is a virtual state? You can say the wave function psi star and psi. I mean, the product of psi star and psi of a virtual state is going to be time dependent. But for a stationary state, the the psi star product of psi star and psi is time independent. You will see that the time dependent part e to the power minus I e t by h, something like is to be there, right? So it is going to be vanish when it is a stationary state. Anyway, so let me add maybe another level, rotational level. As it is plus j equals to plus minus 2, suppose here my, so this is the energy I have provided. This is H mu L. One possibility is that one, it is coming here with H mu M 1, and another possibility is it can come here with H mu M 2. So what kind of energy we should expect? Suppose this is my spectrum. So at 0, here we can get the Rayleigh scattering. What is this? M1. So the energy is, so it has given energy to the molecule. So the frequency of the scattered light is less. So this is Stokes, right? Stokes Raman, Stokes shifted, the Stokes line. And for here, what has happened? The frequency of the light has increased. So this side is anti-Stokes. Are you following? So
Yes, sir. Yes, sir.
if I plot it with increasing frequency, then for a anti-Stokes, I should say for a So this we will see something like this, and here in this case also you are going to see something like this. So this is with increasing nu. So your this is anti strokes because in this case your energy is higher. This is your rally and this is your stroke shifted. Right? Now tell me the gap between this rally and the fast Raman line. Fast anti-strokes or fast strokes. How can one determine this? This is nothing but you remember the rotate. We are only dealing with the rotational levels, right? So energy of the rotational levels is how much? It is B
J into J plus B into J
into
into J
J
plus.
J plus 1 centimeter inverse, right? In this term. So what is suppose this is what is J plus 2? J plus 2 is going to be J plus 2 into J plus 3. Ultimately, it will come the energy gap from J plus 2 to J come something like 2B into 2J plus 3 centimeter inverse for a anti-Stokes. Why anti-Stokes? Uh, J equals to sorry, this is for a Stokes. Why? So tell me, will it be Stokes or anti-Stokes? Because here J is zero
J plus 2
1.
is higher, so that's why
It will be
it is
Stokes.
stopped.
Stokes. And anti-Stokes would be when it is J minus 2, right? From J. That would be minus 2B, 2J plus 3, something like this will come. So obviously, fast line will come at a distance of from 0, it would be how much? J equals to 0. So that is 3, 6B. Fast gap is 6B magnitude. And then onwards, the gap is going to be equal on both the sides. And that gap is going to be 4B, right? Because the next line will come as 10B, right? 1. So 2 plus 3 is 5, 10B. Then it would be 2, 2, J equals to 2 is 2 into 2, 4. 4 plus 3 is 7. 7 into 2B would be 14B.
Yes.
Then it would be 18B. 3 into 2, 6. 6 plus 3, 9. 9 into 2B, 18B. And that way, again, in case of rotational spectra, what we have seen, the gap between the line was 2B. And in for the rotational Raman, the gap between each of the rotational spectra is now 4B. So suppose there is some question coming from rotational Raman, so don't you have to be very careful. Now you can't work with 2B. Now you have to work with 4B. And you also have to be very careful that which transition they are saying. Are they saying the gap between Rayleigh and the strokes or anti-strokes, or in between the anti-Stokes lines or the Stokes line? So if they are talking about this the gap between the fast transition and the relay, then it would have been 6B. So one have to be very careful while doing the numerical problems from here. Okay. So
Yes.
so this is one of the concept. Now for vibrational Raman, it is I think it can take I guess any value. I am not sure the selection rule. I think the selection rule was plus minus one or any value. Do you remember for vibrational Raman what is the? I think it is plus minus one only, or it can take any value.
I think it can take any values.
Huh. But there is a catch. There is a difference between the vibrational
Yes.
Raman
At
and that is only coming due to the population thing, right?
population inversion at room temperature.
Not population inversion. That is due to
Sorry,
the
population.
population
Sorry,
population
population at
Boltzmann
room.
distribution, right? your energy difference is very high for vibrational levels, right? So most of the population is at v equals to 0. And here your population is the could be highest at here in any intermediate j, right? Depending on the it mostly dependent on the degeneracy 2j plus 1. But in case of vibrational, that thing is not there. Only the mostly the highly populated state is the v equals to z 0.
Yes.
So in that case, the main difference is that you are only going to see the Stokes line, not the anti-Stokes line. So what I'm trying to say, the intensity of the so if I think of like as a band structure, something like that, as a Stokes shifted plot. Suppose these are the lines I'm going to get. Obviously, this is my uh, your Rayleigh scattering. I am going to get almost no anti-Stokes lines. Okay, so that is for vibrational Raman, but you can get vibrational, yeah, even anti-Stokes line by the Carr spectroscopy, right? Coherent anti-Stokes Raman spectroscopy. What you do there, that obviously at room temperature, what you do that when suppose your first you are going to a virtual state and then it is coming back to suppose here. Now what you are doing, you are exciting for the first time, not only once, but exciting for here also. So what will happen now? It can come either to this or this. So then you can see Stokes and anti-Stokes both. So that is known as coherent anti-Stokes Raman spectra. That is known as CARS. This is one of the way to get vibrational Raman anti-Stokes vibrational Raman spectrum. Another thing we are going to discuss is that in this here that's the cross section of the transition, and it is going to be for a Raman for a normal electronic transition. So so what is actually happening here? It is going to be for a Raman spectroscopy. There are two integrals are required, right? So there are two transition are taking place. One is first your psi I to your virtual state, and then you from your virtual state to your final state, right? And these are the alpha, beta, or alpha, gamma, whatever you want to take. These are your uh, uh, it is not dipole moments, but your induced dipoles, right?
Yes. Yes.
This is your induced dipole moments. And obviously, these are x, y, z. You can take the charge out, and then only the coordinate will be there. Anyway, and it is going to be square of this. Not only this, but also there is delta E minus h nu. This term is there, right? So this is your, so the denominator, what does it actually mean? So these actually mean that if the gap between, so what is this? This is the gap between the states. So if first of all, one thing, the Raman lines or the transition lines doesn't really depend on the excitation wavelength. Why? Because it doesn't really depend on the position or the energy level of the virtual state. You can excite it to any virtual level, still the gap is going to be the same, right? This gap and this gap are not dependent upon which virtual state you are uh, exciting your molecule to on the first state, right? It doesn't depend on that, because anyway it will go there and it will come back to here. This is the difference that is going to matter. So that's why Raman scattering doesn't depend on the excitation spectra. the position of the Raman transition. Why I'm trying to say that, I'll give you some later after, just after this slide, I will show you some Raman spectra data, not the Raman spectra which is useful for the Raman spectroscopies. Sarah was discussing, right, that for the fluorescence spectroscopies, the Raman spectra is actually a nuisance, and for Raman spectroscopies, the fluorescence signal is a nuisance. This is the exact term Professor Datta has used. I will show you why he told it like that way. I will show you some data. So for a very weakly emissive sample, the Raman signal is actually going to be very effective. So that's what I'm going to show you. So when delta E is going to be very, very close to your excitation energy, that time your denominator will be very, very small and your cross section will very blows up, right? So it will be close to 1. So that's when you are going to see a very highly intense Raman spectra, and that is known as your stimulated not stimulated. What is this known as? Wait, resonance Raman spectra. Okay, because delta E and H nu are very, very close. The gap is very, very less. Okay, now with that, let me show you some. So one data I'm going to show you. So mostly I deal with the fluorescence spectra. So I'll not go into the deep of the data. I don't think it is visible. Is it visible right now?
Yes, yes, sir. It is
Yes.
visible.
So right now, actually, I'm trying to show you some electronic spectra. Just focus on the red spectra. Huh? The red spectras are fluorescence, or for this case, these are emission spectra or the fluorescence spectra. Okay. See, for this molecule is these spectra are for different solvents, and these are uh, so these are the molecule names. So first of all, this panel is for R1, one molecule, R2 is different molecule, R3 is another molecule, like that. R5 is different molecule. Now, if you see only this row, the upper row, you can see one difference. See, this is only the fluorescence spectra, this is fluorescence. Now, for R5, can you see one peak here? Some peak is coming here.
Yes, yes. Small,
Yes,
small peak.
small peak is coming. Now let me tell you, my R1 is very, very emissive. When I go from R1 to R5, my emission quantum will actually decreases very much. Okay, so that's why that in R5 we can see in the emission spectra itself, the Raman scattering is coming. You can also see the same thing for this molecule DBMPT in acetonitrile or in methanol. Even you can see the Raman scattering in methanol, acetonitrile, DMF for R5 ethyl acetate, these cases also. These peaks are actually Raman scattering. Okay. So it actually depends on the, I told you the transition doesn't depend on the excitation wavelength. Okay. But what I tried to mean is that so if I so for this molecule I have excited I think at 480 nanometers, something like that. Okay, at the excitation or absorption maximum, and then I collected the emission spectra. So suppose I have excited it here and I got it the Raman spectra here. So this is actually the Stokes Raman, right? So we are right now dealing with the electronic levels. So obviously we cannot see the, and we this is wavelength. So this side will be your Stokes line. So these are your Stokes shifted, or this is Stokes Raman spectra. This spectra. Now how can you, so emission is very, very less. That's why you can see this many noise. Okay, and see here the emission is for the left hand side, it is very highly intense emission was there. That's why the spectra was very clean. But in these cases, for the polar solvent, these are, the molecules are actually solvatochromic molecules. So for these molecules, you can see the spectra are very noisy because the emission itself was very, very less. And as the emission was very, very less, you can see the Raman spectra. Now you can say that you can see Raman spectra. Even though this is very, very noisy, why can't we see the Raman spectra? Actually, for this, I have for this spectra, I have excited at this point at 300, something like that. There is no particular reason. So when I have excited it here, what happened is that your uh, the Raman spectra position actually depends on where you are exciting. So and that actually that doesn't come from your solve yeah come from your uh, sample, because your concentration of the sample is even very, very less. This is coming due to your solvent. It is so the position of the Raman spectra. See, for DMF, acetonitrile, and these cases, they look very close, but still there is some differences there in the position. So that is because the solvents are different. Okay, so the Raman scattering, what you are seeing, these are not from your molecule. This is coming from the solvent.
Okay.
So and it depends where you are exciting. If you excite it here at 300, then it will come something around 350 or 450. Then you won't be able to see it. That's what happened for this molecule. I have excited somewhere here to get a clear, as it was already a very noisy spectra. So what I wanted to get, it is a Raman free. So as Seth said that for us, fluorescence spectroscopy, Raman spectra sometimes become nuisance because strong Raman spectra is problematic. So that's why I have removed it by exciting it some other wavelength. Okay, so just to give you a just an idea what Raman spectra in fluorescence spectroscopy looks like. That's what. That's why I showed it to you. I hope you got some idea. Um, Next, how much time is left? We have half an hour. We can actually discuss some more numerical problems. I have collected some rotational spectroscopy problems. These are from Banoel book. So is for now. So the symmetry part we'll discuss maybe on the next day. But for do you have any other query from the Raman spectroscopy part?
No, sir.
Okay. So now maybe we can discuss this microwave, some more numerical problems. The first question is a microwave spectrometer capable of only operating between 60 nanometer, 60 centimeter inverse to 90 centimeter inverse was used to observe the rotational spectra of hydrogen iodide and deuterium iodide. Absorptions were measured as follows. For HI, three rotational lines are given. For DI, four rotational levels are given. Actually, based on the as the spectrophotometer is capable to work between 60 to 98 centimeter inverse. So from here, what you can get the 2B between HI, that is coming something around how much? 5, uh,
12.8 something.
yes, 12 point, it would be, yes, 12 point, let me do it once, 5, 7, 8, 5, 12.855, something like that. I hope I have done it correctly. And maybe for this, how much is the gap? Is it the same? 5, 5. Yeah, 12.85. This was easier. So you can see obviously the 2b, those are actually equal. So from here you can get the b, right? B of hi is how much? It is
7.
6.4275, right? Something like that. And for di, what is the 2b? It is something like 705.6, right? It is something like this centimeter in the, yes,
Correct, sir. It is 6.
correct, right? Yes. Then the b would have been 3.2535, something like that. So this is what. So as you can see, your we know what is b. B is 8 8 pi square IC. So, and not only IC, I can write it in terms of 8 pi square mu r square C. So, between HI and DI, what are the difference? The mu is different. Only mu.
Yes. Mu.
And mu of DI is high, right? So, that's why the rotational constant is smaller for DI than the HI. And what approximation we are taking, that the bond length are actually same. So if you try to now, so what are the next question they are asking? So they are saying that find B, moment of inertia, and bond length of each molecules. Okay, and determine the J values between which the transitions has taken place for the first line for each of the molecule. Okay, so first of all we got the B value, right? Now I'm not going into the I and R. Maybe you can do it for as a homework. But what about which transition are those? So for the transition, what do you know? So this is one of the transition they are saying. So how can we know? So suppose the transition is from J to J plus 1. Obviously, because your delta J is plus minus 1. So your that would be 2b, and the gap would be 2b into J plus 1. So that is your 64.275, the first line, right? You know 2b is 12.855, J plus 1, 64.275. So what is J plus 1? Mm, it is close to 5, right? It is actually 5. Okay. So if your J plus 1 is 5, then the transition was from 4 to 5, right?
Yes. Yes.
Yes. Now, if that is the case, then this part is done. What about this? This is, let me actually write to b dash into J plus 1 is 65.070, and 2b we know is 6.507 into J plus 1. So J plus 1 is 10, right? So the transition was from 9 to 10, right? This one,
Yes,
rotational
sir.
level 9 to 10. So that's how you can do it quickly. And when you actually, I will ask you to not only go for the I, moment of inertia, but also try to calculate R. When you calculate R, then only you are going to see what assumption do you take in the first place, that the bond length are going to be the same for both the isotopes. Means both the molecules with different isotopes. For HI and DI, the bond length are going to be same. This is the one approximation we took. See, we have the value of B right now. We know what Planck constant is. We know pi. We can calculate mu, right? The reduced mass. We know the speed of light. So obviously we will be able to calculate the bond length for each of the HI and DI, right? Try to calculate it, and then the question actually that states that support do your results support the usual assumption that the bond length is unchanged by isotopic substitution? Try to look for this answer, that
Okay, sir.
what is going to be the difference between the two bond lengths. For a spoiler, let me tell you, obviously, as we took the approximation, the gap is going to be very, very small. But how small, that you try to see. If it is, means can we, if our assumption is valid or not. That's all. Okay. Maybe we can go to the next question. This question actually says that sketch a diagram similar to figure 2.7. The figure 2.7 from Banoel's book was a sketch of your population versus your rotational levels or rotational quantum number. So that was the sketch. So what they wanted us to do is that using rotational constant B is equal to 5 centimeter inverse and a temperature of 1600 Kelvin, sketch that diagram, that uh, population versus your rotational levels, rotational quantum numbers maybe. So it would look like something like if your, sorry for the poor drawing. So this is your values of J are increasing this side like this, and this is going to be your population of the jth state. Okay. Now see what they have said. Note, find the maximum and calculate 2 or 3 points on the either side. Do not attempt to carry out the calculation for every value of J. So they have said the find the maximum. Do you remember the formula of maximum? First of all, the population was
Over of
dep-
yes.
yes, yes, yes,
Root over of J max is equal to root over of KT by 2 HCB minus half. 2 HCB
minus
minus
half.
half.
Very good, very good. So and your this formula is something like 2j plus 1 exponential minus ej
By
by
KT.
kBt, and something ej was, if I write it in terms of, so it will be b j into j plus 1 into hc, right? Because ej is in joules,
Yes, yes.
and kb value, you know, Boltzmann constant, you got the temperature. So first you need to see that where your maxima is going to be. So kb is how much? 1.38 into 10 to the power 23 joule Kelvin inverse. Temperature is 1600 Kelvin. Then 2 into 6.626 into 10 to the power minus 34. Then B is in centimeters, so obviously we are going to take 3 into 10 to the power 10 centimeter second inverse into B is how much? 5 centimeter inverse. So centimeter inverse centimeter gone. Your Kelvin gone. It is joule seconds, right? Joule gone. Second inverse gone. Minus half. Don't forget this. You will see it will come something like 10.5. Something like that will come. and this side is minus half, you will see that I'll not say this will exactly come as 10, but it will be close to 10. Okay. Why this thing is happening? Why it is not? Why are you not getting the exact point? Why are you getting something 10 point something you are going to get? Because your J is quantized, right? Your J is quantized, but we are using so this is your population, right? And what we are suggesting is that if this is the population, what we are actually doing? We are doing dpj by dj is going to be 0. This is the differential equation we are using, right? We
Yes,
know
yes,
what pj is, and then we are differentiating with respect to j and giving it a value of 0. Then we are getting some value where there is a where there is, the slope is 0. That means it is either maxima or minima. Most of the cases it is going to be maxima. For that you also have to take your second derivative also. Anyway, uh, what we are doing a differentiation. And when can we do a differentiation? We can do a differentiation when our uh, function is continuous, right? But here our
yes,
function is not continuous. So as j is quantized, pj is also quantized
yes,
population. So that's why this kind of 10 point something is going to come. It is the maxima is not always going to be at some value. So you have to see that how far it is from one of those integers, and then only you have to take that value. Okay.
yes,
So by that way we can calculate that j max is 10. First of all is that, and then you try to so we have this equation. You try to calculate P10, P8, P9, P11, and P12. Okay, you try to calculate this first. You calculate BHC by KBT. You calculate this first, huh? You are going to get some, at 1600 Kelvin. You are going to get, I guess, something like 0.45 or something like that. I'm not sure. So try to calculate. Let us actually calculate. B is what? B is 5 centimeter inverse. So 5 into H. H is 6.626 into 10 to the power 34 minus 34. Then into C. C is 3 into 10 to the power 10. Then divided by KB. KB is 1.38 into 10 to the power minus 23 joule Kelvin inverse. So your joule got cancelled above your centimeter inverse got cancelled. Your second and second got cancelled, and here is your temperature is also going to get cancelled. Yes, it is coming as 0.0045. Okay, so you calculate this and then you put your, so what is going to be your P10? P10 is going to be 2 into 10 plus 1, 21 into e to the power or exponential minus, see j into j plus 1 is there. J is 10. 10 into 11 is 110 into BHC you have already calculated 0.0045, right, by KBT. So try to see what is going to be the value. So suppose this is my 10, this is a 9, this is 8, this is 11, 12. So you try to get, so you are going to get some value here. And this is the maximum value. Obviously, then you will see some decrease from here and some decrease from here, but I'm not sure what are the value of P9 and P8 you are going to get. That obviously P8 will be less than the P9, but if P9 is more than P10 or a P11 or P12, that I don't know. For roughly, I'm drawing something like this, but you try to see what are the exact values. The diagram will sketchily it will look something like this. Okay. So from here, what are the concept that we understood? That obviously the rotational the population will go over a maximum value always. Why? The first part, the part before this actually is dominating thing is 2j plus 1. That's why it is an increasing function. And then afterwards, from this part, it is going to be something like exponential. So the exponential term is going to be the dominant factor after this maximum population. Okay. Up to this maximum population, this degeneracy was the main factor. So you try to determine the values and to see what kind of graph you are going to get. Okay.
Yes,
So,
yes.
so I think this was the last question. Another thing I have. So, so this is the molecular spectroscopy question paper from 2024. Professor Datta's question is this. He has set this question for a mid-semester examination. Obviously, for this year, the mid-semester examination is already conducted. Uh,
So
similar
can
kind
you
of
please
question.
share? Can you please share the question paper?
Yeah, yes, you are currently seeing the question. So you can. So anyway, you are going to get this question in the notes, right? In the note, you are going to get the slides and the notes. You can either take a screenshot now or maybe you can do it later. See what kind of question he gives. So bond length, some easy question with some derivation also. So this was a mid-semester exam, right? So obviously this is not going to. So for your NPTEL exam, it is all going to be your MCQ or MSQ. You don't have to do any derivation or such like that. But generally in questions, for understanding the concept, professor actually gives this kind of derivation kind of question, as you can see that 1C. Acha, first tell me. So I will actually solve this question on the next day.
Okay.
Okay, we'll solve it together. You see the question paper. The first part and the second part is also here.
Okay.
Uh, so you take a screenshot and then you try to solve it. We will try
Yes.
to solve it together on the next day. I will collect the mid-semester question paper for this year also, and then maybe I'll share also that one also. So almost similar, but you see, the question number 1B is very tricky. The question number 1B, how many actually how we or how will the spectrum of the molecule in question number 1A change if the temperature is lower to 0 Kelvin?
Okay. Everything will be at ground state.
Mhm.
All the molecules are in ground state. Supposed to be in ground state if it is tending to zero at
Why that
such lower.
2J plus 1 factor is there na?
Yes, 2j plus 1 is there. Yes.
Then your exponential term KBT T
That will
is 0,
that that
infinity
will go up.
0.
Yes, that will go up.
That so that will blow up. So e to
And
the power minus infinity. So that would be 0.
yes,
That would
0
be 0
multiplied by
means
something.
here, yes,
Yes.
0 multiplied by your 2j plus 1 is also going to be 0.
Yes.
So your molecules, all the molecules are going to be
Ground
in
state
the
at
ground
ground.
state. But
Yes.
how your spectrum will look?
If all the molecules are in ground state, then it's like means there is no transition.
There is no
Not
transition or there is going to be one transition? only one transition is going to be take place, right? Because delta J equals to plus minus one. So
Yes.
if your molecules, all the molecules are in your J equals to zero, then only J equals to zero to J equals to one transition is possible.
Okay.
And you also have to write the position of the transition. So from there you can see that I think spacing between the two successive lines are 8 centimeter inverse. So obviously it is also going to be. I think the transition point would be how much? 2b into j plus 1, j is 0, so 8 centimeter inverse. So you are going to see only one transition
Okay.
at 8 centimeter inverse.
Yes.
Then you are going to get the full marks. If you say only one spectrum, then you are going to get half marks. Actually,
Okay.
I was the TA for that course, so I knew the number breaking and those things. I know. That's why I'm telling.
So NPTEL question will be different from this actual question.
Yes, yes. Because as you see, the for this type of question, there are multiple. See the next part. You can see there are multiple derivation kind of questions are there, right? So in NPTEL question, you can't expect in MCQ how would you going to solve derivative kind of question. So some questions from the concept will be asked,
Okay.
but not exactly. You can't really write for one page. You are bound with one or two options only. One,
Okay.
two, three, or even four options.
Yes.
Multiple correct, right? So see,
Yes.
the question number 2C is about you don't have to. So we are not going to solve the derivative kind of questions because we have already discussed those. See, question 2C is about that Fermi golden rule
Yes.
that prove that the rate of the probability and see all the things have been given. Most of the things are given. You don't. One doesn't have to remember each of the things. Most of the things are given. That how the wave function will looks like, what would be the product of that wave function. So see this even up to that Cm star Cm is already given. Right? So one doesn't have to remember and one doesn't have to mark. I remember with this question Cm star and Cm is given, but the students actually marked from the whole derivation. And they started from that psi m psi l. They have determined the expression for cm cm star like that. So I was told that for those kind of atoms give a negative mark because they have marked it up.
Okay.
Why one have to start from the beginning if the equation
Yes.
is already given? So they have not read the question or they have not understood the question. So, so see, all the things will be given. From here, what you can understand that most of the expression will be given, but you have to remind some of it, but most of the things will be given. The question 2b, try to solve it yourself. We will solve it. Question 2b. Using a Taylor series expansion, the potential energy of an enharmonic oscillator uh, arrive at the energy expression, consider the first order correction. Even
Okay.
question 2a also. Why
Okay.
the fundamental transition of an enharmonic oscillator much stronger than the fast overtone?
Yes.
We'll try to solve it.
Yes. Yes. Yes.
It will be a good exercise. So you take a screenshot maybe, or maybe I will share the slides anyway. So on the next day we'll do it along with the symmetry discussion and all
Yes.
assignment solution. So maybe we can stop it for today. And thank you again for joining.
Good
Hope
night,
the
sir.
session. Good night. Good night.